Okay, here we go. So last time we were talking about doing integrals and polar coordinates. Remember, broad stroke, what that means when you say you're doing an integral in polar coordinates. It means you're doing a change of variables. It's fundamentally a change of variables. We're just using the polar coordinates conversion formulas as a change of variables function. And since that gets done quite a bit, there are some certain conveniences and shorthands that we get to take advantage of, one of which is the stretching factor is always the same. So notice I don't have to compute that stretching factor. I just have to remember to put it in there, right? And the other is, of course, we don't even really have to draw the pullback domain. We can just think about how to slice up the domain that we're given with the understanding of what does a theta slice look like, for example. And theta slices, of course, look like kind of like this. They represent constant values of theta as you kind of rotate through around the origin. Okay. All right. So next example. Now this is a little bit of a weird one. It's a little bit less of a sort of a layup than the previous examples we saw. Here our solid or our two-dimensional region is this thing right here, and notice that is the part of this disk, right, that is not in, that's what this thing here means. That means, let's exclude all of these points. So we take the yellow disk and we take this big red bite out of that yellow disk, and what remains then is our actual domain here called R. Okay, there's our domain for this integral. Is everybody with me so far? Everybody's happy. Okay. So let's start slicing it up. And recall, we always do our differentials in this order. Like practically always, right? And furthermore, we always write down the whole dv all at the same time so that we don't forget our stretching factor. And again, it's, oh gosh, I see this so much every year, right? And I don't want students leaving points on the table, right? I mean, it's so easy. All you got to do is remember to write it down, and the best way to remember to write it down is to remember to write it down as you're writing down your differentials. So please, please make sure to remember that. Okay, now let's do our slicing process. Let's think about our theta slices. Again, slices look kind of like this, coming out of the origin, right? And our first slice is kind of down there, if you will, which gives us just this point. And likewise, our last slice is up here at that point. And so all I need to do is understand what is the value of theta at each of these 2 points. Now, there's a couple different ways you can do this. One thing you could do, for example, is notice that this lower bound point is on both this curve and that curve. You can infer the equations for those curves from these two equations here. You can convert those into polar coordinates. I guess you could do that, right? And then solve for theta in that pair of equations. Fair amount of effort to do it that way. Not the worst thing I've ever seen. But here's the better way to do it. Notice that this and this are both radii of what is known to be a unit circle. And so I immediately know those two lengths are 1. And that's just an easy sort of a freebie observation from the picture we already have. And then furthermore, notice that this is a radius of this known circle of radius 1. And so that distance also 1. And so therefore we have ourselves a nice little equilateral triangle here, and that means that I could just cite old known facts about geometry. I know that angle is pi over 3. And of course, as a coordinate, that means that this angle, let's see, I'll do it like this, representing that point, the value of theta is negative pi over 3 because of which direction it's going. Everybody happy? Neat little slick move there. Okay, now, as usual, we fix a value of theta. Arbitrary choice value of theta. Let's say we pick this one. There's our theta slice. Now we think about the range of values of R, and R starts at, well, whatever it is at that point. So now I got to figure out what is r at that point. And of course, now again, as we've already discussed, that's on the circle of radius 1 centered at the origin. So it's kind of a freebie that r is equal to 1 there. Excuse me. This point here that's going to give me my upper bound, that point is on this circle. And so here, I guess we do have to actually write down the equation of that circle, convert into polar coordinates, and what we find is that it has, whoops, I missed. It has this equation. Here, keep in mind I'm looking for an r bound, and so I solve for r in that equation. And r is 2 cosine theta. Everybody happy? One last little micro detail, and I mean, just don't forget the little micro details, but we do then, of course, have to plug in what our integrand is. Our integrand, you can see right there, it's x. I've got to pull that back through the change of variables function, which is fancy talk for, in this case, just recognize how to write that in polar coordinates. And, of course, x is just r cosine theta. So there you go, and now we have ourselves an iterated integral in polar coordinates, and notice it's a single integral, not the 3 that we would end up if I sliced up this kind of, you might call this an ellipse-shaped domain, right? Relevant callback to, what was that, last week or something? And if you were to slice this up in the usual rectangular way, you'd have at least 3 separate integrals to deal with, each of which would have square roots all over the place. Yes?
Do you mind explaining why dA is dr d theta?
Well, it's dA is r dr d theta, right? And so the idea there is that we're talking about doing a change of variables. We're talking about doing a pullback, and yeah, so we are actually technically doing a pullback into the r theta plane, and the stretching factor that comes from our polar coordinates change of variables function is something that we computed, and it's r. Yeah, is that cool? Yeah. Yes.
Can you explain one more time where you got the upper bound for dr from?
The upper bound from So we are looking at for a given value of theta. So there's our theta sort of slice, right? And we're looking at this point because that's the point with the greatest value of r. That point is on this curve, and I claim that the equation for that is this. Now, how you get that is some work that I didn't write down. I just kind of alluded to. But you have to write down the equation for this circle in rectangular coordinates, which is high school algebra, right? And then convert that equation into polar coordinates, sort of chapter 1 methods. Is that cool?
Yeah.
Yeah, okay, yeah.
Why again is the angle equal to the bounds for pi over 3? Like, how'd you get?
Yeah, so that's just noticing that this right here is an equilateral triangle. Each of these 3 sides is a radius of a known unit circle.
And why does that mean that it can be equal to the point? Like,
What now?
Like, I get that the pi over 3 is the angle.
Yeah.
Why is that like a coordinate?
So what this number needs to be, it needs to be a value of that variable. In particular, the lower bound is the value of this variable on the first one of these slices, right? And if you look at all of your different theta slices, your theta slices look kind of like this, and this is the first one. Does that make sense? Because, keep in mind a theta slice. A theta slice is represented by a ray coming out of the origin, because that's how you measure theta.
Okay.
Right? Yeah. Right. Yeah. Okie dokie. Okay. This last example for polar coordinates is of historic interest. This is a calculation that first got done a couple hundred years ago. It's a famous calculation. It involves normal distributions, and if you've ever had a stat class, you'll recognize this integrand here as being very important for what's called the normal distribution. It's one of the most important distributions in probability. It's fundamentally natural in ways that we don't have time to talk about here, but if you take a stat class, they'll talk about that. Integrals of distributions, or probability density functions they call them, represent probabilities. And so, in related to using this as a distribution to represent probabilities, we need to be able to compute this integral. And what's unfortunate about this integral is that if you follow your usual temptation of, well, I guess I better take the antiderivative first, you run into a dead end because you can't. There is no way, without using power series, to write down an antiderivative of this function. It can't be done. So, problem, right? How are we going to deal with this? And very clever idea. Wish I'd thought of it. I certainly did not. The big idea is to take this integral that I want to compute, give it a name. That's not that impressive. Where the eyebrows get raised is I'm going to not compute j directly. I'm going to compute j squared. Now, you'll notice that this is the exact same integral being multiplied by itself. The only difference is a dummy variable, which of course doesn't matter. So, so we have j squared. How am I going to compute this product? Okay, couple of really clever moves. Please, again, don't ask yourself if you would have thought of this on your own. Right? That's too high of a bar. I certainly would not have. First observation, though. Let's think about this integral, this dy integral. This thing over here outside of it is just j. It's a number. It's a constant. I don't know what the constant is yet. That's kind of why we're here. But it is nevertheless just a value, right? And constants, you can just stick inside of an integral. No problem. It's like a 4, right? It just moves in and out of the integral effortlessly. Okay. Next clever move. Let's look at this dx integral. Notice that this dx integral is inside of the dy integral, dy being further to the outside. As far as that purple dx integral is concerned, y is a constant, which means that e to the negative y squared is a constant. And again, constants, you're allowed to just move inside of an integral. I'm doing this weird kind of folding around of the expression. It seems a little strange to want to do such a thing, but perfectly legal. The point to this, well, the first part of the point is that I have now taken my j squared and I've written it as a double integral. Well, technically I've written it as an iterated integral, and of course we recall that iterated integrals can be are equivalent to the corresponding double integral. Is that cool? Everybody happy so far? It's not clear where I'm going with this or how this is a good thing, but nevertheless, there we are. Okay, yeah. Mm-hmm.
Why is j squared with dx and then with dy?
Yeah, so that things will work out nicely. I could have written this as this one in terms of x and also this one in terms of x,
okay,
but then I wouldn't be able to do the tricky move that I'm doing here. So I'm free to change the variable to whatever name, right? There's nothing magic about the 24th letter of the alphabet.
Sure.
And whatever, I'm just going to use a different letter here. It's legal, right? And the reason that I choose to do it is so that I can generate, by these little tricky moves, an integral in the xy plane. Yeah. Is that cool?
Okay, yeah.
Yeah. Okay, so what? Case could be made that what I've done is I've taken what looks like a hard problem and I have turned that into what looks like a even harder problem. And sometimes that's actually a really useful method in math, as it turns out. In this case, harder though this looks, harder though arguably it kind of is, being a double integral, we have another option on the table for how to compute it. I can compute it in polar coordinates, thus bringing it up at this point in the course. Okay, so what if I compute this in polar coordinates? Who cares? The who cares is, notice that because our area element with that stretching factor has this extra factor of r in it, right? Because we have that extra factor of r, now look at my inside integral. My inside integral here, I still have this scary e to the negative something squared expression, but now I also have this extra little factor of r. It's exactly what I need to be able to do a basic u substitution. And for this dr integral, just let u equal to negative r squared, and it's a relatively easy Calc 1 integral. No problem. And yada, 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 details to be worried about, and what we end up with is pi, not forgetting, of course, that what we just computed was j squared. And that being j squared, don't forget that what we were actually interested in is j, therefore j square root of pi. Yeah.
Why was it introduced as a dummy variable, right?
I'm sorry?
Why was it introduced as a dummy variable?
Yeah, just an alternative dummy variable to x. That's right.
Yeah, but doesn't the conversion x squared plus y squared into r squared assume a certain relationship between x squared and y squared?
Yeah, but that's what polar coordinates is. Yeah.
Wasn't it just a dummy variable based on x? So why are we sure that it did have that relationship?
I mean, I could look. One thing I could have done is instead of using x and y, I could have used like phi and theta, and that would have just left me in a situation where I don't have any recognizable sort of convenient opportunities. So perfectly legal, but that's a road I didn't want to go down. So the clever move that I am copying from my teacher of 30 years ago, right? The clever move is, of all the perfectly legal roads that I can go down, I'm going to go down the one that has good news at the end of it. That's all. Yeah. Yes.
What is the actual significance of like j within the context of normal distributions?
Yeah, it's the value of this integral.
Does that like tell you
the
area under?
Let me be very quick because that's a stat question and this isn't a stat class. The short version is that if you want to have a probability density function, the total integral does have to be 1. And so really what I should do is I should call this k e to the negative x squared, and I should be solving for what value of k would make this integral 1. And effectively what I'm seeing here is I need to divide the whole thing by square root of pi.
Okay, cool.
Yeah.
Do you mind explaining how you got the bounds for the iterated integral, like the 0 to infinity?
Oh, well, yeah, so that's just thinking through the what do we mean by, certainly all of R2 is described by those values of x and y, right? And if you just ask yourself the question, if I want to describe all of R2 in polar coordinates, how would I sort of sweep out the whole xy plane? Well, I would go all the way around, right, for theta, so theta would go 0 to 2 pi, and then for any value of theta, I start at the origin and go all the way out, 0 to infinity. Does that make sense?
So the equivalent of negative infinity to infinity in Cartesian coordinates is
Yep.
0 to infinity for r, and then
Yep.
0 to 2 pi for...
Yes, that's right. Yep. Yeah, last question.
So you just assumed, you just took y just because you wanted to arrive at the conclusion of...
Yeah, I wanted to find myself, if I had called these P and Q, then I'd have DP and DQ, and I just wouldn't recognize that, right? But so you can call them anything you want, and once I have them in this form and having chosen X and Y, then this is literally, no kidding, a straight-up iterated integral out of section 5.4 or 5.3 maybe, I forget, right? But it's just a regular old integral in the XY plane. And that's just familiar and allows me to make this reference to polar coordinates that have already been set up.
So that was intentional.
Oh yeah, absolutely. Okay, we got to go on. Well, ask me after class if you have any other questions. This example is not that important. But I wanted students to see it. But talk to me after class. Okay. All right. Okay, cylindrical coordinates. A lot like polar coordinates. Again, we've already set up most of what we need to do to talk about doing integrals in cylindrical coordinates. We have our change of variables function that goes from r theta z space into xyz space. We've computed our stretching factor. Again, just r, right? And so now we just need to kind of do the same thing, in particular, recalling that we saw polar slices, r slices and theta slices. We saw what they look like in the xy plane. Likewise now, we're going to see this is what cylindrical slices look like in XYZ space. And again, it's kind of the same sort of a deal. Here's theta, for example. Here is a theta slice, namely a constant value of theta, plane perpendicular to the theta axis. Right? And what does that look like in the XYZ space? And, well, it looks like this. Is that cool? Is everybody happy? By the way, the terminology I like to use to explain this is I like to think of this as kind of like being a door, and you kind of imagine these half planes kind of swinging around the z-axis, kind of like a door swinging around its hinges. So sometimes I'll describe this as a half plane hinged on the z-axis. It just kind of hits that metaphor for me. Okay. And you can do the same thing with R slices. We're actually not going to need to do this as it's going to turn out. We'll see why in just a moment, but nevertheless, a constant value of R, this is what that would look like. It's part of a kind of a part of the side of a cylinder. Okay. All right. So when we're doing cylindrical coordinates, good news, again, with the 6 different options that we have for the differentials, these are the only 2 that you'll ever need, practically speaking. And I suppose I could manufacture some really unnatural example that would be to the contrary. But in practice, day in and day out, you're never going to see anything where one of these isn't as good as any other option. So I encourage you to think only about these 2 options. In particular, notice that this is just basically the dr d theta that we've already discussed in polar coordinates as always being the right choice. So always dr d theta together and in that order. And then the question is, do you put the dz on the outside or on the inside? And depending on the circumstance, maybe one might be more convenient than the other. Okay. All right. Again, don't forget your stretching factor. Again, the best way to remember that stretching factor is to write down this whole dv all at once. After all, this is what you're replacing dx, dy, dz with. This is your dv, your volume element. So please don't make the mistake of writing down your differentials only first, right? And then assuring yourself that you'll remember to write down this stretching factor. Again, the evidence that I've seen shows that most students have a surprisingly high odds of just getting busy and distracted and not remembering to put it back in there. So please write it down all together. You're much more likely to actually remember it. And then again, just with every other kind of slicing that we've ever done, we're going to be looking at bounds on our iterated integrals. There are relevant points that will determine them. Those points will be on various surfaces. Those surfaces will have corresponding equations. Solve for what you want, just like everything else we've ever done. Okay, so example. Got this upper half ball. There. Right, solid. I guess we could do this in rectangular coordinates, but square roots just all over the place, right? It'd be a nightmare. Don't really want to do that. Here's our alternative, one of our alternatives, that is. I'm going to do cylindrical coordinates. Notice that here's my dx, dy, dz. Notice, again, importantly, stretching factor already inserted. Right? You've got to get those points, right? This is worth several points on an exam. Just write it down. I'm arbitrarily choosing this of our 2 standard choices of ordering the differentials. And with that chosen, let's start slicing. We'll start with d theta. So what does a theta slice look like? There it is. Right, that slice of our solid, I make a geometric appeal. Looks like that. What is the range of values? Well, it's going to start over here where theta is equal to 0. It's going to go all the way around, and it's going to end, kind of back at the same spot, but of course, having gone all the way around, that's now 2 pi. So the range of values for theta, 0 to 2 pi. Yeah? Everybody's good? Great. All right. Okay, now, as usual, we fix a theta. We're going to focus now just on this one theta slice. We think now about R slices. What does an R slice look like? An R slice represents a constant value of R. A constant value of R would be, like this. Which looks bad. But the good news is, of course, all I actually care about, I don't actually care about the whole R slice. I just care about how does this R slice intersect my theta slice. And we know this cylindrical slice is, the way it intersects this theta slice is actually pretty simple. It's just this little segment right there. So that's, as far as we're concerned, what an R slice looks like. Okay. So now, first and last. Well, the first one is over here, where I think it's a pretty easy pitch that R is equal to 0. Thus, our lower bound is R equals 0. Let's see, our last slice, let me just get rid of that green there. Our last R slice, as we continue to move along, our last one is going to be a very small little point, R slice right here. What's the value of R at that point? Now, there's different ways that you could go about this. You could recognize it as being part of the sphere, and it's in the xy plane, and you could write down the corresponding algebra. You could solve for R. That's doable. I think it's easier sometimes to just observe fortunate geometry, and in particular, this ball has radius A. That distance that tells me the R I'm looking for is one of those radii of that ball. So it's A. Right? So sometimes geometry, again, is convenient. Missed again. I don't know why I'm missing the thing there. There we go. Upper bound for R is A. Everybody good? Okay. All right. Let's see here then. Okay, last. Now again, with a theta fixed, and now furthermore with an R fixed. And so looking just at that slice there, that represents the range of values of Z. And now again, I've got to think about first and last. And well, the first slice, the first Z slice of my R slice of my theta slice happens at that point, which is in the xy plane. That's where Z is equal to 0. So lower bound is 0. Easy geometric lucky break there. The upper bound, and here's where you have to do a little bit of work. That last Z slice, right there. Let's see here. Let me just get rid of the distractions here. That point, notice it's on our sphere. You can write down the equation for the sphere. You can write down what that looks like in cylindrical coordinates. You may recall we actually did this back in chapter 1, I guess it was, a long time ago. So here's that equation for the sphere in cylindrical coordinates. Wait, what were we doing here? Why are we looking at that point? What are we interested in? Don't forget, we are trying to find a value for Z. Right? Like, it's so easy to lose track and accidentally solve for the wrong thing. We're interested in a value of Z, so in this equation I will solve for Z. And that is what gives me my upper bound for my inside interval. Yeah?
Why does theta go 0 to 2 pi?
Why does what now?
Theta, why does it go until 2 pi?
Oh, yeah, so going back to our very first slicing here, the theta, right, this is what a theta slice looks like, and it looks like that for sort of, I'm going to say all the way around, right, for all the values of theta. As I take these theta slices the whole way around, right, every one of these theta slices looks exactly the same and are significant. And so I don't get the whole solid until theta has gone a full turn, which is 0 to 2 pi.
So the it's like on the bottom of the circle, not like
I'm sorry, what now?
Like it's nothing to do with it being a half full. It's like the bottom of the circle.
Oh, if you want to make a projection argument, you could, right? You could think, all right, well, I'm going to, as far as the r and theta bounds are concerned, if I just project down into the xy plane, sure, that'd be a reasonable way to think about it. Yeah. And then in the xy plane, theta goes all the way around. If you prefer, right? I'm just presenting it here as we have a solid, and theta slices means we're taking slices of the solid. Those slices are significant all the way around. Yeah. Yeah.
Can you explain that in Z again?
Which part?
The Z for a squared minus y squared.
Okay, yeah. So, all right. So what we're looking for here is an upper bound for Z, right? So I'm looking for the value of Z on sort of the last Z slice. There it is. Is that geometrically? You buy it, right? Okay, it's on this surface, which you can write down the equation of, sort of, high school algebra, equation of a sphere, right? And this is what that looks like when you convert that into cylindrical coordinates. Now, that's a process, and you've got to go through and do the conversion, right? And keeping in mind that what we're interested in is a Z value, we have to solve for Z in that equation. And that gives you your Z bound. Okay. All right, moving along. Same domain, slicing it the other way. I'm going to be quicker with this one because it's very, very similar. All the same sort of, domain and same surface, etc. The big difference with this one is that when you get around to trying to figure out what your inside bound is, now your inside bound is a value of R. So it's still going to be this point right here. That point is still on this surface. That's still the sphere. It still has the same equation. Everything looks the same, except, very critically, big difference here. Because we are doing our differentials in a different order, we are now interested in a different variable, right? That point, that sort of last value that I'm interested in, that's a value of R. So, same equation, sure, but now I have to solve for R. And it's that R that is our upper bound there. Is that cool? Everybody happy with that? These are the little details that you have to worry about. Easy to lose track of some of these things. Okay, moving to spherical coordinates. Same story. Change of variables. Using the spherical coordinates conversion formulas. We've already computed the stretching factor. We could actually do it as a pullback. We don't want to. The pictures are hard to draw. It's confusing, right? Much more convenient to actually just see what do the slices look like in XYZ space. Just a lot easier to think of it that way. So as before, constant values of theta, right, are half planes hinged on the z-axis because it's still theta. The spherical theta is exactly the same as the cylindrical theta. So that's no change. And, we could write down and worry about, well, what do phi slices look like and what do rho slices look like? And the answer, well, again, constant values of those variables. A constant value of phi is going to be a cone. Oh, gosh, that was terrible. Let's try that again. Less terrible. So that's kind of a strange look, right? A phi slice, a constant value of phi, a little bit weird. Good news, we're not going to actually have to worry about that very much. We'll see why in just a moment. And then, of course, a constant value of rho. Points a given constant distance away from the origin. A really weird slice. I don't know any knives that'll cut like that. Maybe a melon baller. Right? But anyway, that's what a rho slice would look like. And again, good news, this isn't really going to affect us very much for reasons that you'll see in just a moment. Anyway, big picture though, we are going to use the fact that we know what slices look like in the XYZ space to actually do our work. The good news, same tips. In fact, for spherical coordinates, you're pretty much always going to do them in this order. Throughout my whole physics major as an undergrad, I never saw any natural examples that would be better done in any order than this. So just always use this order for your differentials. Don't even entertain any other possibilities. And it's almost unheard of that would ever lead you wrong. Okay. Likewise, when you do the differentials in that order, don't forget your stretching factor. I've said this a million times. I'm sorry about that, but it's so important, and still it's going to happen. Some students are going to forget this. And again, it's points. Don't leave free points on the table. In fact, if you find yourself on the exam with 10 seconds left on the exam, and you haven't even started the spherical coordinate integral question, just write this down. You'll get several points, possibly 5 points, right? Just memorize this. Rho squared sine phi d rho d phi d theta. Boom. Points. So I think this is, again, a really valuable trick. Write that down all at once. It'll help you to not forget that stretching factor. Okay. And again, the usual process for finding bounds. The only difference between spherical coordinate integrals and cylindrical coordinate integrals and polar coordinate integrals, slightly different geometry. That's it. Everything else is morally the same. Okay, starting with this example here, we have, for our domain, a ball. You might say sitting on top of the XY plane at the origin. So it's centered on the z-axis above the XY plane, directly above the origin. Cool? Okay. All right. Okay. Theta slices look like this. What does that actually cut? Like if I take this theta cross section of our solid, well, we get a half a disk like this. Is that okay? Okay. Now, what's the values of theta for this? Well, our first such slice is going to look kind of like this over here, where theta is equal to 0, and then it's going to go all the way around and end at the same place. And so 0 to 2 pi. What do you think? Yep.
So is that just always true for a sphere?
No, it's always true for a solid that I'm going to say kind of envelops any part of the z-axis. Right, so we've got here part of the z-axis that's embedded inside the interior of our solid. Right. This sphere happens to do that, and other. Ball. I guess I should say ball. Other balls that we've seen do that. Not all balls do. In fact, the very next example won't. Okay. Yeah. So it's not about whether it's a ball. It's about whether it sort of, fully encloses part of the z-axis. Yeah. Yes.
Does it have to have rotational symmetry about the z-axis?
Oh no. No, definitely not. Yeah. No. That. The non-symmetry will be dealt with by what happens, for a given theta slice. How will those phi and rho bounds depend on theta? And sometimes they do, sometimes they don't. In this case, they don't, but in some cases they do.
So would you just separate the integral into a multiple area integral?
I mean, if there's some sort of a if there's a need for that, but there isn't always a need for that. Yeah, sometimes it's just the dependence is that the phi bounds are functions of theta, and then that what the nature of that function is sort of takes care of that automatically. Yeah, right. Okay, so there's our theta slice. Now here is an artistic option for you to think about. You don't have to do this, but this theta slice. The slice being this shape right here. Notice we're kind of looking at it in a weird way. We're looking at it at an angle. It's geometrically awkward. Most noticeably, this is a right angle in real life. It doesn't look like a right angle. It looks like an obtuse angle the way I've drawn it. That's confusing. Right? And it can lead you to getting wrong answers sometimes. So look, my little hack to get around this, and this is just this is highly optional, you don't have to do it. I like to just take this theta slice, that whole little plane deal, and just kind of redraw it where I'm looking right at it from sort of straight on. And now notice that what is in fact a right angle in real life is also drawn as a right angle. It looks like a right angle. And so a little bit less confusing. When you're thinking about theta bounds, a little bit less confusing to look at this picture. And just keep in mind, it's just a reproduction of what this is, just, kind of drawn a little bit more conveniently. Yeah?
So the reason that's just pi over 2 is because the sphere is not centered at the origin, so it's not...
Oh, you're ahead of me. You're down here?
Yes.
Yeah, that's the point. Yeah, ultimately. But we'll wait till we get there. Yeah, that's all right. That's all right. Everybody okay so far? Okay. So yeah, up to you if you do this little trick, the little redraw thing. You don't have to. I find it useful myself. Okay. So let's see here. Let's take our theta slice and let's start looking at phi slices. Keep in mind, phi is measured from the origin. Reminder, here's the origin, right? Phi comes out of the origin. What I do see very often, super common mistake, leads to terribly wrong answers, completely inappropriate, is students somehow get it in their mind that rays should come out of the center of whatever they're looking at. And that's just not how it works. So students end up thinking sometimes that phi slices look like this. And they don't. That's just wrong. Phi is not measured out of the center of whatever you happen to be looking at. It's measured out of the origin. Right? So keeping that in mind, these phi slices here, the first one is like that, where phi is equal to 0. Right? And then you can start looking at your various phi slices, and there's a phi slice, and then as phi increases, it keeps going like this. And then it keeps going, and you'll notice that as I keep going, they're getting shorter and shorter and shorter and shorter, but they never really quite go away until I get to pi over 2, and that's where you have your last phi slice. Anything beyond pi over 2 is just a total swing and a miss. There's nothing down there. Does that make sense? Does that kind of answer your question?
If the sphere was centered at the origin, it would be 0 to pi.
It would. Yeah, that's a totally different question, though. Yeah. Yes.
And it doesn't need to go like past pi or like or in a negative direction. We're only talking about...
I see what you're saying. Yeah. So you're thinking about like. Let's see here. Let me draw this. Here's our theta slice, and you're wondering about sort of if I were to extend that over to the other side. Yeah. So we will get there. We will get there for, instead of this value of theta, we will get there for this value of theta.
That's how we'll get all the way around.
That's right. Exactly. And now, why does it matter? Tempting to say, well, you guys, why don't I just let theta go from 0 to pi? And then I'll get to these. I'll get that whole cross section all at once, and these values of phi would give me those, and then the backwards values of phi would give me the other side. And it's tempting, but it violates one of the rules. You may recall we made a promise to ourselves way back here. Golly, that was a long time ago. Wait, no, I went too far. Way back here. We're only going to choose values of phi between 0 and pi. And the point to that is so that I can get rid of these absolute values.
Right.
And so you got to be really, really careful about that kind of thing. So tempting, but it doesn't work. Yeah.
Technically, could you do it and then make sure that
You could do it, but you'd have to break up your phi integral into two separate integrals, and then there's really no advantage. Yeah, I would never encourage that. All right. Okay. Oh, I went too far. Here we are. Okay, 0 to pi over 2. I think everybody's good with that. And now we fix a value of phi, right? So theta already fixed, and now we're going to fix a value of phi, let's say like this, and we want to know what's now is the starting and ending values of rho. And so now a slightly different picture here, looking at my phi slice of my theta slice. There's my first rho point, and that's at the origin, which is where rho equals 0. So kind of a freebie. Nothing to it. Gotta love it when the geometry is convenient. And then let's see our last value. And here, this is a little bit annoying. That point right there is our last rho value. It's on this curve. But wait a second. Why is there a curve? The original question didn't have any curves in it, right? And so what you have to do is remember. Oh, why isn't this? There we go. You got to remember. Let me get rid of my mess up here. That curve is that curve. So when I say that the point is on that curve, what I'm really saying is the point is on that sphere. And now again, this is an old Algebra 2 question. How do you find the equation of a sphere in various center and radius, etc.? You write that down in rectangular coordinates, and you can then convert that into spherical coordinates using techniques from Chapter 1 from this course. And this is what it ends up being. Now, again, I'm going to skip over that algebra. Make sure you can do that. That's stuff we did a while ago. And again, this is a good practice problem. Try to do exactly this one, and this is the answer that you end up with. Okay, and with that done, keep in mind what we're interested in here is we're looking for values of rho. So within this equation, I need to solve for rho. Lucky break, it was already in that form. You get lucky sometimes, but not always, right? We've seen examples where it wasn't. Having already gotten it in the right form, there's my upper bound for rho. Everybody good? Oh, yeah.
Would there be any reason to do d theta before d phi?
I have never encountered one.
Okay.
Yeah, I think it's I mean, as far as the slicing point of view goes. Sometimes for algebraic purposes, once you get it written down in a certain form, yeah, maybe. But for the kind of thing that we're going to be looking at, there's just really no reason. I would always put theta on the outside. Yeah. Right. Okay, yeah.
So phi and rho are always measured from the origin?
Yes. Yeah, that's right. Yeah, exactly. Yeah. Okay, now I've made the following pitch before. I'm going to make it again here. I think this is an appropriate time. Notice the 3D picture drawing was pretty critical in these problems that we've done in cylindrical coordinates and in spherical coordinates. And so that's an important skill to develop. Most people are not born being really good at doing 3D drawing. Right? It's just, we can quibble about whether some people might be naturally less or naturally more inclined toward that sort of thing. It doesn't matter. Everybody needs to practice it. And practically everybody who hasn't already had the advantage of seeing it needs to know that there are certain techniques that really make a difference. So I urge you to, don't try to reinvent the wheel on this, right? Find the good techniques. Again, I have videos on my miscellaneous topics playlist that have all the techniques that I know, right? All my hard-won lessons that lead me to being able to do, whatever level of drawing this is, right? Are in that video. Videos, plural. So please make sure to learn the techniques and practice. Again, this is a chops kind of a thing. You need to put in some time and practice, and I certainly did when I was in college. I put in a lot of time practicing drawing just so that I could do this kind of thing better. Okay. A few other things. Now, just real quick observations. Don't try to make your picture teeny tiny. I get a lot of postage stamp drawings on exams, and it's really hard to make sense out of it. Not only is it hard for you to understand what's going on by looking at a teeny tiny picture, it's hard for me to make sense out of what you're communicating with your picture. And keep in mind, the purpose of a picture is twofold. It's to help you understand what's going on, and it's to help me understand what was happening inside of your head. Right? I need to be able to understand your thought process. So make it a nice, big, clear picture. Don't try to do it all at once. Revise and redo, I think, is really important. You will have scratch paper, of course, on the exam. Use that scratch paper for, among other things, drawing a bad picture that you can then learn a little bit from and improve with a second draft, which you can then learn a little bit from and improve to make a hopefully pretty decent third draft, maybe fourth if necessary, right? But don't expect that you should be able to just see it in your mind and then just draw it and have it be beautiful. That's not really, I don't want to say it's not realistic, but it's certainly not realistic for everyone. Right? So please take all this seriously, and I fear I may be out of time now. Let's see here. Yeah, I am out of time. Okay, well, we will draw the line right here and pick up here on Friday. See y'all later. Have a good rest of your day.